Welcome, students. Today we're going to break down the chapter on solutions. Now, this is a super important topic, not just for your exams, but for understanding so much about the world around you. तो बच्चों, चलो शुरू करते हैं.
So, here's our game plan. We'll kick things off with the absolute basics, then get into how we measure solutions. After that, we'll look at solubility, then jump into the really important stuff like Raoult's law and colligative properties, solve a problem together, and finish up with a super fast revision.
All right, let's start at the very beginning. Before we can talk about anything else, we have to nail down one simple, fundamental question. What exactly is a solution?
Well, this picture pretty much says it all, doesn't it? A solution is just a homogeneous mixture of two or more things. Now, homogeneous is just a fancy word that means it's perfectly and uniformly mixed. Think about it. When you stir salt, our solute, into water, our solvent, poof! The salt disappears. You can't see the individual particles anymore because it's all become one single thing.
Okay, so in this story, we have two main characters. First, you've got the solute. That's the stuff that gets dissolved, and it's usually the one you have less of. Then you have the solvent. It's the one doing the dissolving. You have more of it, and it decides if the final solution is a liquid, a solid, or a gas.
Now here's where it gets really cool. We usually think of solutions as a solid dissolving in a liquid, right? Like salt and water. But look at this table. You can have all sorts of combinations. You can have a gas dissolved in a gas. That's the air we breathe. You can even have a solid dissolved in a solid, like metal alloys. So solutions are literally all around us.
Okay, so now that we know what a solution is, we need to know how to describe it properly. Just saying it's a little sugary or it's very salty isn't good enough for science. We need numbers. So how do we express exactly how much solute is packed into a solution?
First up, we have molarity, and notice that's with a capital M. This is probably the one you'll see most often. It's really simple. It's the number of moles of your solute divided by the total volume of the entire solution in liters.
And next, we have molality with a lowercase m. Now, be very careful here because this one is different. It's the number of moles of solute per kilogram of the solvent only, not the whole solution. So molarity is about the final volume, while molality is about the mass of just the solvent you started with. It's a subtle but really important difference. यह formula अच्छे से याद कर लो. And finally, there's mole fraction. The easiest way to think about this is like a percentage, but for moles. It's just a ratio. It tells you, out of all the moles in the mix, what fraction belongs to the solvent and what fraction belongs to the solvent. And remember, for a simple solution with two parts, their mole fractions will always add up to 1.
Now, let's switch gears a bit and explore something really interesting. Why do some things dissolve better than others? And in particular, let's look at a very common case, dissolving a gas into a liquid.
For this, we have Henry's law, and it gives us a really simple but powerful rule. All it says is that if you crank up the pressure of a gas above a liquid, more of that gas is going to dissolve into it. The formula, P equals KH times X, just puts that idea into math, connecting the pressure P with the amount of gas dissolved, which we measure by its mole fraction X. More pressure, more dissolve. Simple.
And this isn't just some boring textbook law. You see it in action everywhere. It's the reason your soda is fizzy. They pack that CO2 gas in under super high pressure. It's also why scuba divers have to be careful when they come up to the surface, and why mountain climbers can get sick at high altitudes, where the low pressure means less oxygen dissolves in their blood.
Okay, let's get to the real heart of this chapter. This is where things get fascinating. We're going to explore what happens to a solvent when you dissolve something in it. How does adding a solute change everything?
These changes are called colligative properties. And here's the most important thing to remember. They don't care about what the solute is. They only care about how many solute particles there are. It's all about the numbers. It doesn't matter if it's salt or sugar. It's the quantity that counts. Let's look at the 4 big ones.
First up, when you add a non-volatile solute, that's just something that doesn't evaporate easily, like salt, it actually lowers the vapor pressure of the solvent. You can think of it like the solute particles are getting in the way, blocking the solvent molecules at the surface, and making it harder for them to escape into the air as a gas.
Now, if you've lowered the vapor pressure, what does that mean for the boiling point? Well, something boils when its vapor pressure matches the pressure of the atmosphere. Since we've lowered the starting vapor pressure, we're going to need more heat, more energy to get it to boil. And that's why we see an elevation or an increase in the boiling point.
And on the flip side, the exact opposite happens with freezing. The solution will now freeze at a lower temperature. This is called depression in freezing point. And it's exactly why we throw salt on icy roads in the winter. The salt mixes with the ice, lowers its freezing point, and causes it to melt, even if it's below 0 degrees outside.
And last but not least, we have osmotic pressure. This one might sound a little complicated, but the idea is simple. It's the amount of pressure you need to apply to stop the natural flow of a solvent across a special barrier called a semi-permeable membrane. This is a huge deal in biology. It's how plants get water from the ground and how our own body cells stay balanced.
Okay, all this theory is great, but the best way to really understand it is to put it into practice. So let's try applying these formulas to a typical exam question. Samajh aa gaya? Let's give it a shot.
Okay, here's our problem. We're dissolving some sodium sulfate in water, and we see that the freezing point drops by a certain amount. What we need to find is something called the Van't Hoff factor, or I. Now, I is just a number that tells us how many pieces a solute breaks into when it dissolves. So for sodium sulfate, we expect it to break into sodium ions and sulfate ions, so I should be more than 1. Let's calculate the exact value.
So, let's break this down. First step, we calculate the molality of our solution. Easy enough. Step 2, we use that molality to calculate the theoretical change in freezing point. That is, the change we'd expect if the solute didn't break apart. For the final step, we find our I by simply dividing the real value we observed by the theoretical value we just calculated, and we get our answer, 2.63.
Wow, we have covered a lot of ground today. So before we wrap up, let's do a super quick revision to make sure all these key ideas are locked in.
This mind map is a fantastic tool for revision because it shows you how everything is connected. We start in the middle with solutions, and from there we branch out to the basics, the different ways to measure concentration, the laws of solubility, and finally, the big one, the colligative properties that depend on all that other stuff. Use this to help you study.
So I'll leave you with a final challenge. Now that you're a solutions expert, I want you to look around your own home. What's happening when you make a sweet cup of tea, or when your parents add salt to boiling pasta water? Can you explain what you see using what you learned today? Think about it.